In part 2 of this lesson series on memory, we learned about system consolidation. And this is the idea that after an experience, the memory for that experience gets reorganized across different brain regions, the hippocampus and the cortex. We also said that this was perhaps related to what's happening when an episodic memory is transformed so that the contents of that learning episode can be stored in the semantic memory system. In this lesson, we'll use diagrams to try to help us understand a bit more about the details of this process. First, the standard consolidation theory. Now, this has been challenged recently, but it's a good place to start. So let's say here we have our hippocampus and the cortex, and this brain is undergoing some learning experience. Well, the hippocampus is going to respond and make a memory trace. So here we have our icon for the memory trace formed in the hippocampus. And this is a robust change in synapse strengths. So we have a hippocampal memory trace here. Now, we said in the last lesson that scientists think that the cortex, of course, is also processing the learning episode, but the nature of the changes here are not as significant as in the hippocampus. In other words, this memory trace may be weaker than the memory trace in the hippocampus. Now, the importance of the strong hippocampal memory trace, scientists believe, is that it serves as an index or a pointer to retrieve the memory of recently learned information. So the hippocampal cells are sort of making a memory trace of the event, and then can be used upon, when the memory is retrieved, they can reactivate the cortical memory trace. And that's what would happen during memory retrieval for recently learned information. But over time, scientists hypothesized that this process of consolidation, what it was doing was strengthening the cortical memory trace. So that now the cortical memory trace is strong enough that it can support retrieval without the need for a hippocampus. So if the memory trace gets strengthened in the cortex, this is the semantic memory system, other retrieval systems would be able to retrieve this memory without the need of the hippocampus acting like a pointer or an index or a little kind of handle to reactivate a memory. Once consolidation happens, then the cortical memory is strong enough to support retrieval without a hippocampus. Now, standard consolidation theory made some important claims that have been challenged. The idea here was it's the identical memory for the event that is simply, in a sense, moving locations. We had a hippocampal memory trace, we had a weak cortical memory trace, and what happens over time is kind of a shift in the strength of the memory traces, so that now the cortical memory trace gets strong, and you don't even need the hippocampus anymore for retrieving this memory. So the idea was it was the identical memory of the event, it's just stored in the cortex, and the hippocampus cortical links are not required for episodic memory once it's consolidated. There is recently some controversy over this point, and the question basically, is the hippocampus necessary for vivid, detailed, context-specific episodic memories? Now, the standard consolidation theory says no, that once consolidation happens, you no longer need the hippocampus to retrieve them. This has been challenged. The new idea, trace transformation theory, says that the hippocampus cortical links are required for context and detail-rich episodic memory retrieval. So no matter the age of the memory, if you're going to relive the experience, you need a hippocampus. And furthermore, what gets stored up in the cortex is not the identical memory that was sort of stored in the hippocampus, but it's the transformed memory. It's that difference between sort of the episodic type of memory and a semantic type of memory. So in trace transformation theory, consolidation is a process whereby a memory is transformed from a detail-rich and context-specific memory into a more generalized version of the memory that can be integrated with other stored information in the cortex in semantic memory. Even episodic memories become more schematic, more semanticized, but they are then hippocampus independent. So again, here's an episode. We're making a hippocampal memory trace. The initial cortical memory trace is weak. Consolidation involves this transformation where the cortical memory trace gets strengthened. But if we're going to have access to the episodic memory, we still need the hippocampus to retrieve the detailed episodic memory. Nevertheless, we can store a kind of a semantic version of that memory in the semantic memory system. So over time, then what's happening is that the episodic memories are providing information to be stored in semantic memory. And so we can have both kinds of memory. We can have access to detailed and vivid and context-specific episodic memories, but we can also have a more generalized version of that memory that we have integrated into the semantic memory system. It's the semantic memory, though, that is hippocampal independent. On the trace transformation theory, we will always need the hippocampal system to retrieve detailed episodic memories. In trace transformation theory, the hippocampus-dependent version of the memory and the cortical version can coexist. The demands of the moment determine which memory is retrieved. So for example, if somebody says, what do you know about amoeba and paramecia? I can activate the cortical memory, the semantic memory system here, and retrieve information about amoeba eats paramecia. If somebody says, do you remember the day in class when you learned about amoeba paramecia? That's going to require then the reactivation of the hippocampal memory trace. And then I can pull up those details that it was the day before Halloween, I was in my costume, etc. So we can have both of these kinds of memories, and the demands of the moment may determine which kind of memory gets reactivated. But for trace transformation theory, all detailed episodic memories are going to require an intact hippocampus. In fact, if the hippocampus is lost or damaged, then the cortical gist-like version of the memory is all that can be retrieved. So let's take our example of knowing information about this couple and then also having episodic memories. Well, if after storing all this information about this couple, if I lose my hippocampus, I'm going to lose access to these episodic memories. All I will have left are semantic memories of that couple. So I might be able to tell you that they enjoy reading and tennis and dancing, but I will fail to be able to retrieve a vivid, detailed, context-specific memory of these episodes. In this diagram here, the idea is that each of these episodes would be a different sort of context involving the couple, and when I consolidate all this information, I'm storing the general information about the couple in my semantic memory system. So I can have information about the couple in my semantic memory system, and it will not require a hippocampus to retrieve that information, the semantic version of they enjoy reading, tennis, dancing. But if I don't have my hippocampus, I cannot relive these episodes in my own personal history that involve this couple. And it should be clear now also that without a hippocampus, then we have lost the ability to make new episodic memories. But since episodic memories provide the content to semantic memory, if we lose the hippocampal system, we lose the ability to store new information in our semantic memory system. Now, why do scientists think this process of system consolidation happens? Well, it goes back to some of the early patients, the neurological patients, that we learned a tremendous amount about human memory from individuals that had either damage to certain parts of the brain or underwent surgery for other reasons that removed parts of the brain, and then scientists studied the consequences for memory. So we'll take a look at that in another lesson.